Hello everyone, we're going to look today at chapters 20.4 and 20.5. So two of the last little sections in the book, they go nicely together. There's not an awful lot for 20.5, so it makes sense to merge it with what we're doing with 20.4. So this will cover today's lesson and also Friday's lesson as well. Now I'll be honest, at this point I've never ever watched The Big Bang Theory. However, if you speak to Mr. Benjamin, he knows an awful lot about it. So through the course of the video, we'll look at the Big Bang Theory and then evidence towards the Big Bang Theory, one of which is MBR, or microwave background radiation. We'll also discuss the idea of the expansion of space-time, as it's known, and then we'll finish off with looking at the evolution of the universe, so how it started and how we think it might end, and incorporated into that, what on earth is the universe made of? Because actually, we don't know an awful lot about it, so we call it dark energy and matter. So we'll look a little bit at that too. So let's start with the Big Bang Theory. Now there's mixed thoughts on this. I always suggest that you go into your exam knowing the times and the temperatures of what's happened from time naught to today. And in your book, in chapter 20.5, table 1 is all of the information that I would suggest you go into your exam knowing. The specification's unclear whether you need to be able to state it. I suggest that you do spend some time making a nice, pretty picture that you can then remember certainly the time and what happened. So what's all this evidence, I hear you ask? Well, we've looked at Hubbles Law already, but there's also this thing called MBR. Now, you're probably too young to remember, but in the olden days, we had to tune our television. And in between channels, we would see that picture just here. So it's that fuzz. And what science tells us is a small percentage, about 2%, of this interference is caused by microwave background radiation. On the top right, you will see 3 different pictures, and the latest one there is Planck 2013. But what it is are different telescopes looking at the universe, and the colour represents the temperature. Now, if I had a scale on here, one of the things that you would see is, although there's a slight variation, the temperature actually is very similar in all parts. So you can see the resolution gets a lot better compared to the one in 1992. So it's thought that in the early universe, the Big Bang, so clearly huge amounts of energy, gamma rays were certainly very much in existence, just linked to E equals HF, high energy, so high frequency, hence gamma. And then as the universe got bigger, so as it expanded, the waves have also done the same as well. Apologies if you can hear the rain in the background, it's lashing it down. So when we start, the waves will be a small frequency, and then over time they expand, and it's such that now they've expanded so they're in the microwave region of the spectrum. And then that's why when we turn our TV on, certainly the old-fashioned TVs, then you get that interference because the microwaves from space are of a similar wavelength to the ones that we use on television. So the early universe was extremely dense, but also very hot. And linked to that would be gamma rays, but now it's cooled down. The temperature that's associated with that is 2.7 Kelvin, where 0 Kelvin is absolute zero, the coldest temperature that you can get. We'll do more on Kelvin when we look at the next topic, which is going to be thermal physics. So this radiation that we can see in the background from space could not be explained by any other theory, and therefore the Big Bang Theory became the most widely accepted theory of the origin of the universe. Now, I think we've touched on this on a previous video, but it's worth mentioning again because it's mentioned in 20.4 in the book. So if we assume that the universe has expanded uniformly, so just like when you blow up a balloon, all sides expand at the same rate, the reality is slightly different. So we know that we've got it accelerating rather than uniformly, but we do know V is roughly equal to H naught D, so Hubble's law. So then by rearranging, so V over D equals H naught, or D over V equals 1 over H naught, so I'll just flip that round and put a 1 over H naught. If we do some maths, what we can see is the age of the universe is equal to the inverse of H naught. So once you've found out what H naught is in seconds to the minus 1, you can then get an answer of about 14 billion years. Now, whilst this is very much an approximation, there's quite a large error, plus or minus, with that. It certainly gives a very good approximation, and the error mainly is because the universe is accelerating rather than expanding at a uniform rate. So moving on from this, we don't actually know an awful lot much more in reality, and supposedly we only understand about 5% of our universe, and we know so little that we've had to make up new terms called dark energy and dark matter. Most things that we use to measure in physics have a mass, so we can weigh them. They might have a charge, so we can use the idea that they might deflect, or we can use electromagnetism and magnets to deflect. Whereas some things, and we're saying dark energy and dark matter, have neither of these things, or if they do, they're so hard to detect, we just don't have the equipment available. So anything that we don't understand, we put the word dark in front of it, because when we look at how galaxies rotate round, we can visualize how much stuff is there because of the light that's given off. But the physics doesn't really work. So things are rotating at different rates, or they're moving at different speeds, that when you look at those universal laws of physics, they only work if something else is there as well. So, as I said, we don't know much more than this. In your book, in chapter 20.5, figure 1, the pie chart is given, so you can see that we can account for only a very small proportion of everything that we need to exist in order for all of the physics to work, to make our understanding better. So at this point, it's probably worthwhile doing a bit of research and typing into Google a little bit about dark matter, and then the difference between that and dark energy. Or if you're being lazy, then you can see that dark matter definition is there in the simple terms, and dark energy simple definition is just there. But certainly please spend some time looking at the difference between the two and getting as much information written down ready for your notes as possible. So the last little bit in your book on chapter 20.5 just refers to the idea that the universe is accelerating, and we believe that it's accelerating because when we look at stars or galaxies that maybe are exploding, they don't behave as we would normally expect based on our current understanding of physics. So the term dark energy was coined, and it's our best current theory or hypothesis to explain that the universe is expanding at an accelerated rate, but we can't currently detect it. So is it there or isn't it there? It fits the purpose for now. And as with a lot of things, as we get more information, as technology improves, as scientists share that information, then it will get disproved and a new one will come along. But at the minute, all the evidence suggests that it probably does exist. We just don't really know much more. So that leaves us with probably many questions about the universe because we don't really know, but there are lots of theories out there. So please do spend some time looking at other things, such as the shape of the universe. So some people say it's a saddle shape, some people say it's spherical, some people say it's flat, and there's different terms that you can look at, not necessarily as part of your specification, but you might find of interest. Equally, you might have heard of the Big Crunch. Well, what is it? And linked to that is, will the universe contract? Will it carry on expanding? What's going to happen over the next 13, 14 billion years? Anything? Will there be another Big Bang? Have there been previous Big Bangs? And then with all these things, what are the conditions that need to be met? And a lot of it is determined by the amount of matter that's in the universe, and then therefore what gravity does. So if there's too much matter, then gravity might pull together more because there's more mass. If there's not very much mass, then maybe gravity isn't strong enough. So we might carry on getting expanding. So there's quite a lot here for you to research and hopefully just try and understand a little bit more about the topic, but not necessarily that's relevant to the course, but just something that might satisfy your curiosity. And then in addition to just doing some general research, please do complete 20.4 and 20.5 summary questions. And now we've finished chapter 20, there are plenty of practice questions for you to have a go at. Please let me know which questions you struggle with well in advance of Friday, please, so that I can then potentially create another video going through any of the questions that you have struggled most with. So please do feedback so that I can then give you some feedback. So ideally, no later than the end of play on Wednesday, so that I then have a bit of time, maybe Wednesday evening and Thursday, to create something for you to look through on Friday.